Pulling a sled on snow. The forces applied to the sled are tension force, gravitational force, normal force, and friction force. Tension force is an internal force and is present when you pull on the rope. The tension force allows the sled to be pulled forward. Gravitational force is present because of the weight of the sled, which pulls it down towards the ground. The frictional force opposes the sled's motion and causes it to slow down. The normal force is the force that the ground has on the sled. This force is perpendicular to the surface and it balances out the gravitational force acting in the opposite direction, so the downward direction. The surface introduces the force of friction, which opposes the pulling motion and causes the sled to slow down. If the surface is rough, it has a greater force of friction that resists the motion. As such, you need to pull harder on the rope to overcome friction and move the sled. Compared to the other forces, snow is not rough, causing it to have a low friction. Since snow has a low friction, there is less resistance to the sled's motion, thus making it easier to pull the sled. However, grass and dirt have higher friction, meaning that it opposes motion more, making it harder to pull the sled. Newton's first law of motion states that if an object is in motion, it will continue to stay in motion unless another force acts on it and causes the net force to be unbalanced. The law also states that if an object is at rest, it will stay at rest. This law applies to the sled's motion. If the sled is at rest and not moving, then according to the law of inertia, the sled will stay at rest unless there is a force that causes it to overcome the inertia and move. On the other hand, if the sled is moving, it will keep moving at a constant speed in the straight path unless the friction or applied force causes the sled to speed up or slow down. If the sled moves at a constant speed, it is evident that the force of tension is balanced by the force of friction, acting in the opposite direction. When these horizontal forces are balanced, that means that F net equals Ft minus Ff equals ma, which equals 0, indicating that there is no acceleration. The vertical forces, force of gravity, and normal force are balanced as well. However, if the sled just starts moving or speeds up to a certain constant speed, this implies that the forces were balanced at first. In this case, the sled speeding up is caused by the tension force being greater than the force of friction. As soon as the sled reaches a constant speed and stops speeding up, then the forces become balanced. The box starts off at rest, but when you push it, it begins to accelerate because its speed is increasing from a resting position. Although there is a static friction acting on the box while it's at rest, once an applied force is strong enough it overcomes that static friction and causes motion, the visible movement of the box. According to Newton's second law, F equals ma, force equals mass of acceleration. The greater the applied force, the greater the acceleration, meaning the harder you push, the faster the box moves. For example, if you push the box with 5 newtons of force of the first time and 15 newtons the second time, the box will move faster the second time because you applied a larger force, which is 3 times more. When the pushing stops and friction is still acting on the box, it will eventually slow down and come to a stop. The main forces acting on the box are applied force and friction force. This is because when you push the box, you are applying an external force to the box, causing the box to move from its rest position. Due to this, applied force is present. In addition, friction force is also present because you are pushing the box on a flat surface, rough or smooth. When you are pushing anything on a flat surface, unless it is specified that the surface is frictionless, there will always be friction force present. However, the amount of friction force depends on the type of surface. Because if the surface is rough, there will be more friction force acting on the box compared to if the surface was smooth as there will be less friction force acting on the box. The force of gravity is obviously also present because gravity is what is keeping the box down and on the surface. If there wasn't gravity, then the box would be floating around. That is not the case. Normal force is also present because it is perpendicular to the surface and is opposing the gravitational force. If there wasn't normal force and there was gravitational force, then the box would just go through the surface. That is not what is happening, and we know that there is gravitational force, so there has to be normal force. In conclusion, applied force is what causes the box to move and causes the box's motion. The friction force is what slows down the box and resists the box's motion, causing it to stop. The gravitational force is what keeps the box on the surface and prevents the box from floating. The normal force balances out the gravitational force, as the normal force is always opposing the gravitational force. The normal force is important because without the normal force, the gravitational force would take over and make the box go through the surface. But the normal force pushes the box upwards to balance the gravitational force out and make sure that the box remains on the surface. If the box's mass was heavier, its inertia would increase as well. We also know that applying the same amount of force to a larger mass would result in less acceleration, as explained by Newton's second law. This is because acceleration depends on mass, and if the mass increases, then the acceleration decreases when the force is applied due to their inverse relationship. To further explain this, if the box becomes heavier, it will accelerate more slowly and move at a slower pace. You would need to apply more force in order for the box to accelerate as fast as before or faster, since greater force is required to push a heavier box. Also, if the surface was rougher, the frictional force would increase. With more friction, you would need to push the box even harder to achieve the same or greater acceleration compared to a smoother surface. This is because more applied force is needed to overcome increased friction before the box can even start moving. In other words, you will need to push the box with more effort and force in order for it to move and accelerate, whether due to its heavier weight or the rougher surface. If you push the box with less force, there will be less acceleration. According to Newton's second law, force equals mass times acceleration. As such, the box may move slower or not even move at all if the friction force is much larger than the applied force. However, if you push the box at an angle, the force has both a vertical and horizontal component. The horizontal component will push the box forward, whereas the vertical component will pushes down on the box. Assuming that you're pushing downward at an angle, the vertical component pushes the box into the floor. Since the vertical force is given by F sine theta, there is more vertical force, which causes the normal force to increase. An increasing normal force causes friction to increase through FF equals mu n. Since the horizontal force is given by F force cos theta, there is less horizontal force. Due to less horizontal force and more friction, the box will move slower and become harder to slide across the surface if it is pushed down at an angle. Real life scenario: a car stops at a traffic light. Buckle up, ladies and gentlemen, because today we're going to be talking about a real life scenario when a car slows down and stops at a traffic light. When a car slows down, there are three main forces that act on it. The first force is the braking force, which comes from pressing the brakes. When you press the brakes apply pressure to the wheel, causing it to rotate slower and making the wheel slow down. Friction is essentially the grip between the tires and the road. when the brake is applied, friction works with the braking force to slow down the car by opposing its motion. It turns the braking force into stopping power. This means that if there is no friction, the brakes wouldn't work to slow the car down. Inertia tries to keep the car moving forward, but the braking force and friction force must overcome the car's inertia, which is not a force, to make the car slow down and bring you to a stop. Guys, when you're in a car or when you're driving a car, and when you come to a stop and your car suddenly stops, why does your body suddenly go like this? Why does your body suddenly move forward even though the car is stopped? And now I'll be explaining the reason and the physics behind this. From Newton's first law of motion, we know that an object in motion will stay in motion unless it is acted on by an external unbalanced force. This is proven when a car is in motion and comes to a stop, your body will still move forward with the same speed even though the car stopped moving. This is because Newton's first law of motion, inertia, as inertia causes an object, car in our case, which is in motion, to remain in motion unless acted upon by a force. So when the car is in motion and suddenly comes to stop, inertia would come into play, as it will make our body feel as if it wants to keep moving forward because the car's motion was moving forward until it stopped. Therefore, due to inertia, when your car's motion is moving forward, then comes to a stop suddenly, your body will move forward even after the stop. That is why you feel a force pushing you forward when the car stops, even though it is actually the law of inertia acting and making your body continue to move in the forward direction while the car is slowing down. You may wonder what eventually stops your body from moving forward, and what is the unbalanced force that stops you from continuing to move forward because of inertia. The answer is your seatbelt. As your seatbelt helps counter this issue because it will stop your body from moving further forward and will restrict your body's movement. If you are sitting in the front seat, the dashboard will also help you stop moving forward as an additional unbalanced force, especially if you aren't wearing a seatbelt. And if you're sitting in the back seats, the driver's seat and the passenger seat will act as an unbalanced force to help stop your body from moving even further. So ladies and gentlemen, remember, this is why you should always remember to wear a seatbelt. If the road was icy and there was less friction, the car's motion would change when it tries to stop. This is because friction acting on the car's tire with the road is what helps the car to slow down and stop when the brakes are applied. However, when the road is icy and there is less friction, the car won't be able to slow down and come to a complete stop as fast, because the car will slide and will continue moving forward for a longer period of time before it comes to a stop. In summary, the car's motion will change when it tries to stop on an icy road, as the car will slide while moving forward even after the brakes are pressed or applied, and it will take a longer period of time to slow down and come to stop than it usually would on a normal road. By relating the concepts of physics to real-world scenarios, I now understand the role that different forces like gravity, friction, normal force, and applied force have in causing or resisting motion. For instance, from the sled and box examples, I realized that friction always opposes motion, and the applied force needs to be large enough to overcome it. I also learned the applications of Newton's laws in everyday situations. For example, the first law, inertia, helped me understand why objects resist changes in motion unless an external force is applied. This explained why the sled stayed still or why the car keeps moving forward unless the brakes are used. The second law shows how force, mass, and acceleration are related, as seen when pushing a heavier box. The third law helped me understand action-reaction pairs in these scenarios, Gaining an understanding of these forces help me explain how and why objects move the way they do. For example, why a box lies slower on carpet. This assignment helped me connect what I learned in class to real life situations, giving me more purpose and meaning to what I'm studying in this course.